Now, we're going to do the same problem, but with the right figure. The couple M is applied to a beam of the cross-section shown in a plane forming an angle beta with a vertical. Determine the stress at point A, point B, and point E. So we realize that our moment is not aligned with our reference axis. So we'll have to decompose it. And so we'll decompose it like this. Now, what is the angle here? Well, this is 30 degrees. We're assuming this is 90 degrees. This will be 30 degrees. So we'll say the 100 times the cosine of 30 degrees. That'll be 50. I want to 50 square root 3. And this one will be just 50. But let's go in order. So the first thing we want to realize is that the formula that we're going to use to find the stresses at points A, B, and D are, or is, minus mzy over iz plus myz over iy. And we've explained elsewhere why there is not a negative sign on the second term. So now, the first thing I like to do is I like to look at the form and say, what do I need? Well, I first need these. Find the moments of inertia about our reference axes y and z. And so how are we going to do this? Well, if you go to the moment of inertia table for a semicircle, you'll see that iy will be equal to iz, which is going to be equal to 1 over 8 pi times r to the fourth. Now, r is 20 millimeters, so we'll do pi 20 to the fourth divided by 8. So let's do that real quick. Pi times 8 divided by, not times 8, times 20 to the fourth divided by 8. And that gives us 62,832 millimeters to the fourth. Okay? So then we go to step 2. And step 2 is we need these. So decompose the moment along our reference axis. So we decompose the moment along our reference axis, and we get what? Well, we get mz is going to be 100, as we were saying earlier, times the cosine of 30 degrees, which is equal to 50 square root of 3. 50 times the square root of 3, which is 86.8. 86.8 Newton meters. And it's pointing along the positive z-axis this time. And now for y, that's just going to be 100 times the sine of 30 degrees, which is 50 Newton meters. Again, pointing along the positive y direction. So then we do part 3. And we realize, well, I still don't have my distances. So what we're going to find the distances of the points of interest with respect to each axis. So say, for example, I want to find A. What is the distance from Y? Well, that's going to be a Z, and it's going to be the radius, right? This is the radius. So this is 20. So it's going to go in the positive Z. So ZA is going to be 20 millimeters. What about ZB? How far is B from the Z axis? And the confusion here is you get confused with the letters. So because you're looking at a distance and the axis. So this is a Z distance. So I think I got that right. Z is equal to 20 millimeters, Z for A. But what is the distance Z of B from Y? 0. And what is the distance D? ZD from Y is negative 20 because it points in the negative Z direction. So we'll do this in white. So what about the distance of A from the Z-axis? Well, that we need to find where the centroid is. And to find the centroid of that, what we want to do is we want to go to the centroid table and locate that the Y for the centroid is 4/3 R over pi. So let's do that real quick here. 4/3 R. I won't put the units. Over pi. So 4/3 R, which is 20. 4 times 20 divided by 3 times pi. That's going to be 8.49. 8.49 millimeters. And so my A is going to be at minus, my YA is going to be minus 8.49 millimeters. My YD is also going to be at minus 8.49. And my YB is going to be at what? Well, it's going to be the radius 20 minus 8.49. So the radius minus 8.49, 20 minus 8.49, that's 11.51 millimeters. Okay, so now in part 4, we apply the formula for unsymmetric bending. So sigma at A is going to be what? Well, sigma at A is going to be minus mz, which we said is 86.6 times what? Times my y at A, which is minus 8.49, divided by 62,832. And then we have a plus. The other part is a 50. Now our Z for A is going to be 20. So really we could write this as this and just 62,832. So that would be for A. For B, we'd have the moments are the same, area moment of inertia also. What changes is the distance. And so for this would be 11.51 and 0. And then for the point D, that would be what? We still have the same moments and the same area moment of inertia, but we're going to have, for our Y, it's going to be minus 8.49. And for our z is going to be minus 20. So we now input these things into the calculator. Let's see what we get. So we're going to do the minus open parenthesis 86.8 times the negative of 8.49 plus 50 times 20 divided by 62832. And what I get is what? I think, let me see real quick. I think I made a mistake on the IY. No, I did not make a mistake on the IY. And the IZ, maybe I did. Oh, the IZ is not the same as the IY. If I look at it, we'll see for a semicircle. That I have to shift. I have to shift the I. And so this is something that's kind of interesting. So my IZ is not the same here, so sorry if I confused you. Let's look at this real quick. You see how we are the neutral point, sorry, not the neutral point, the centroid is on the y-axis. So we don't need to shift that. But we need to shift the IZ. So IZ is going to be IY, but then we're going to have to subtract with the parallel axis theorem that distance from C to AD, which we said is 8.49 millimeters squared times the total area, which is going to be pi times 20 squared over 2. And the reason why we're subtracting is because we're getting closer to the actual center, so our moment area of inertia is going to diminish because the overall distribution of area around the centroid is at an average of less distance on average. So we're going to do 62832 minus 8.49 squared times pi times 20 squared divided by 2. And that's going to give us 17,542 millimeters to the fourth. So I apologize for the confusion there. So we cannot do this. We need to divide by different denominators. So the I sub y is 62832. And 62832. The I sub z is 17,542. And so now let's do this real quick. So that's going to be 86.6 times the negative of 8.49 divided by 17,542. It's really 543 if you round it properly. And then we're going to have plus 50 times 20 divided by 62832. 62832. And we get, what do we get? We get 0.057 megapascals. And that's, let's see. So let's see in terms of units, we have the newtons multiplied by millimeters divided by millimeters to the fourth. And then we have meters that must be converted because there's a meter here. So that would be, we convert everything to, we got to convert everything to millimeters if we want megapascals. So this is not megapascals. And so here, I'm going to multiply everything by 1,000 millimeters every 1 meter. And it's going to be the same here. So you always want to check your units to make sure that they are consistent. Otherwise, you make mistakes. You don't want to make mistakes on the test. And so we do this, and we get 57.8 megapascals on the first one. On the second one, what do we get? Let me change real quick that to 11.51. We get minus 56.8. And the last one, and so you got to specify this is in tension, this is in compression. The last one is going to be what? Well, we're going to have minus 8.49 there, but a minus 20 here. So that's going to be a 26.0 megapascals in tension. So I hope this was useful. It is nice to understand this, so be careful. Be careful on your axes and what you have in your sheets. And then everything else is the standard procedure. And now the last thing is, remember that you might be asked about the angle that the neutral axis forms as well with respect to the moment vector. So since that formula gives it to you with respect to the z-axis, then you have to do some arithmetic. All right, I'll see you next time.